Euclid Maths, Euclid Maths, Euclid Maths.
Welcome back. In this part, we are going to learn how to find directional derivatives in the direction of a specified vector. Finding tangent planes and problems on directional derivatives will be next time. Just enjoy the lecture.
In this present lecture, our main focus is on the directional derivative of a scalar field. I also teach the tangent plane. Of course, at last, we solve a few problems on these concepts. Now, let us understand a classical definition of the directional derivative of a given scalar field. For this purpose, let us select a scalar field f from R3 to R. This function f from R3 to R can be represented as w equals f of x comma y comma z. Also, it represents a surface in the 3D space. Now, we want its directional derivative in the direction of a prescribed vector, say u cap. We very well know that dou f by dou x is a directional derivative in the direction of x-axis. Similarly, dou f by dou y and dou f by dou z are directional derivatives of f in the directions of y-axis and z-axis respectively. But here we want the directional derivative of f in the direction of the given vector, say u cap equals u1 I cap plus u2 j cap plus u3 k cap. This vector u cap can also be represented as the triplet u1 comma u2 comma u3. Now we want a directional derivative of the given surface w is equal to f of x comma y comma z in the direction of our prescribed vector u cap. Here we require the direction of u cap only, but not its magnitude. So we discard the magnitude of u cap. We don't want its magnitude, so we take u cap to be a unit vector. Now let us choose a reference vector x naught comma y naught comma z naught in the domain space R3. Let this point be P. Now let us draw a curve C from this reference point or an initial point, say P x naught comma y naught comma z naught to some other vector x comma y comma z in the 3D space. The direction must be in the direction of our prescribed vector u cap. Now, the curve is parameterized by using a parameter s. Now what happens? At the initial distance or displacement, x of 0 becomes x naught, y of 0 becomes y naught, z of 0 becomes z naught. So these three give the values of x of s, y of s and z of s at s is equal to 0 at the initial displacement. After that, x of s equals x naught plus u1s, because after the displacement s, we reach the point un, so x of s becomes x naught plus u1s. From x naught, we travelled s displacement in the direction of u1, so x of s equals x naught plus u1s. Similarly, y of s equals y naught plus u2s, and z of s equals z0 plus u3s. The directional derivative of our scalar field f maps R3 to R in the direction of the given vector u cap equals u1 I cap plus u2 j cap plus u3 k cap is given by the formula df at u cap equals df by ds at u cap equals limit s tends to 0 f of x0 plus u1s comma y0 plus u2s comma z0 plus u3s minus f of x0 comma y0 comma z0 upon s. The symbol for the directional derivative of f in the direction of u cap is df sub u cap or df by ds sub u cap. If we carefully observe the formula of the directional derivative df at u cap for the function f from R3 to R in the direction of the prescribed vector u cap, we can understand one thing. This formula df sub u cap equals limit s tends to 0 f of x0 plus u1s comma y0 plus u2s comma z0 plus u3s minus f of x0 comma y0 comma z0 upon s resembles the differentiation formula d f of x by dx of a function of single variable in our calculus. Now, let us understand a process of finding the directional derivative of a given scalar field in the direction of a given vector. We can't apply the classical formula to find the directional derivative of a given scalar field in the prescribed direction. So we need a working process to find the directional derivative. So we have to understand the following remarks. Let us select a scalar field f from R3 to R. The directional derivative of this function in the prescribed direction u cap is given by del f sub u cap equals df by ds at u cap. By using chain rule, it can be expressed as dou f by dou x times dx by ds plus dou f by dou y times dy by ds plus dou f by dou z times dz by ds. This can be written as del f at u cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dotted with I cap dx by ds plus j cap dy by ds plus k cap dz by ds. I have already written the directional derivative df at u cap as a dot product of two vectors I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z and I cap dx by ds plus j cap dy by ds plus k cap dz by ds. To evaluate this, we need to find out the values of dx by ds, dy by ds and dz by ds. Let us find out these values. Dx by ds is nothing but the derivative of x of s with respect to s. We have to use the differentiation formula for the function of a single variable here. So we have to find out dx by ds by using a formula for differentiation for the function of a single variable because x of s is a function of a single variable s. So dx by ds equals limit s tends to 0 x of s minus x of 0 upon s. Here we know the values of x of s and x of 0. X of s is x naught plus u1s and x of 0 is nothing but x naught. If we plug in these values there, we get dx by ds equals limit s tends to 0 x naught plus u1s minus x naught upon s. After cancelling x naught, we get dx by ds equals limit s tends to 0 u1s upon s. This in turn becomes dx by ds equals u1. We need to find out dy by ds and dz by ds also. Dy by ds equals limit s tends to 0 y of s minus y of 0 upon s. This again equals limit s tends to 0 y naught plus u2s minus y naught upon s. After cancelling y naught, we get dy by ds equals limit s tends to 0 u2s upon s. This gives us dy by ds equals u2. Similarly, dz by ds equals u3. Now we found the values of dx by ds, dy by ds and dz by ds. Here dx by ds is u1, dy by ds equals u2 and dz by ds equals u3. We have already found the values of dx by ds, dy by ds and dz by ds. We have to substitute these values in our previous equation 1. Then we get df at u cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dot I cap u1 plus j cap u2 plus k cap u3. Now we get df at u cap equals del f dot u cap. So the directional derivative of the given scalar field w is equal to f of x comma y comma z in the direction of our given vector u cap is df at u cap equals del f dot u cap. While finding the directional derivative of a given scalar field f from R3 to R at a given point P in the direction of a given vector u cap, we follow the procedure. In this procedure, we first find out the partial derivatives of the given scalar field dou f by dou x, dou f by dou y and dou f by dou z. In step 2, we find out the gradient of the given scalar field f. Del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. In the third step, we evaluate this gradient del f at the given point P. In the next step, we consider the given vector u cap. Because we want its direction only, we don't want the magnitude, we find out norm u cap. We find out a unit vector n cap equals u cap upon norm u cap. If we observe, this n cap is a unit vector and the direction of n cap and u cap are same. Now, to find out the directional derivative of a given scalar field f at a given point P in the direction of a given vector u cap, we find out del f at P dot n cap.
I hope you are enjoying our lectures. If you prefer any specific topic, please let me know in the comment box. You can write a mail to us for our lecture notes. Please subscribe our channel and press the bell for notifications. If you like the content, spread the word. Thanks for watching.